ancient age or before Christ, in India specifically, there are a lot of mathematicians, and all those mathematicians were trying to develop some formulae, record some observations, and go around looking for patterns in nature. And all that stuff was basically recorded in Sanskrit language in India. In the Western world, it was Greeks. So these two civilizations were really advanced, and the mathematics which was there in that time was more in the form of verses like a poetry. It happened in the later stages after the medieval period that mathematics became a cold, precise tool to calculate things. And nowadays, the mathematics that we do is basically applied mathematics in which our main aim is to calculate things. But when I talk about the real, the pure mathematics, it's all about poetry, imagination, scenery, visualization, just like literature. So that is what it is all about. And okay, I got a comment. Naveen says it looks like a movie title. Yeah, Naveen. In fact, there was a song called "The Sound of Silence." Sound of Silence, and I was thinking to name it as "The Shape of Mathematics" from the movie Shape of Water. So of course, it looks like a movie title. Now, uh, oh, good evening, Nihar from office. Cool, cool. Yeah, this time is I know a lot of people are working and all cannot view it. Probably people would view it after the session goes in recording phase. So let's start with it. What will we learn today? Now, this is a question that today, what are we going to do? The first thing that we'll be learning is Hemchandra sequence. Hemchandra sequence. Okay, before starting this, I'm telling you something. This session is for mathematics enthusiasts who love mathematics and also people who don't love mathematics and they feel mathematics is so boring or so difficult for them. I'm trying to make you interested in the patterns which are spread across the universe. So this is what I'm going to do here. We won't be discussing much questions in this class. We'll basically be discussing about the mathematics and its beauty. So Hemchandra sequence is the first thing that we'll be discussing. Then we'll have Fibonacci sequence. I think if some of you are computer engineers, you might be aware of this Fibonacci sequence. You must have written a program in C back in your standard 12th or 10th for Fibonacci sequence. Then we'll be talking about golden ratios. It's very important and very beautiful thing. And then the last will be how beautiful is beautiful. How beautiful is beautiful. So people who love humanities, love poetry, literature, movie cinema, same thing, music, songs, painting, all that stuff. Just raise your hand, show me a thumbs up that you guys love this aspect of academics. And here I'll be drawing a link between the poetry, the humanities, the arts, and the mathematics. That is what I intend to do over here. So show me your thumbs up in case you are into this magical world of poetry and arts. Cool. Now talking about the first topic is Hemchandra sequence. This painting is of Hemchandra. Someone drew it. And Hemchandra was better known as Acharya Hemchandra. He was a poet and a mathematician. A poet and a mathematician, right? And I'm getting a very interesting comment. Manoj says, we were never taught logic from childhood behind the application of mathematical concepts. I think that is the reason people like me have the fear, no interest in for maths, sir. Good. Manoj, today you will be developing an interest. Like you'll enjoy this same way as you enjoy a movie or a song. So this is what we are going to do over here. This guy, he was a poet as well as a mathematician. Now, some people feel that how can a person be an author, a poet, a painter, and a mathematician? But I'll tell you what, mathematics was basically done by philosophers and writers in the old age. Even Leonardo da Vinci was a physicist and a mathematician and a poet. Right? DS, Rajput, Cat में biography से direct questions नहीं आएंगे, but in an RC there can be. I just gave you an idea. We won't discuss much about this. We'll be discussing the sequence that he created. He was born in 1088. This is there's a reason that I have mentioned the date in a Jain family. Now coming to the Hemchandra sequence. So before starting the main agenda of this class, I would like you to share this session to as much people as possible. I'm live on YouTube as well. This is going to create some real interest. And for this, for uh, teaching you the Hemchandra sequence, I would require a guitar. So I'm bringing a guitar, just wait for a while. Till then, share this with your siblings. This is for everyone, you know, this is open to everyone. I'm just bringing the guitar. चाहिए चाहिए Yeah, so here I have brought the guitar with me. I won't be playing a complete tune, so don't think that I'm going to perform in front of you. I won't do that. But for this Hemchandra sequence, this is very important. I'll just show you something. Well, so on this slide, as you can see, I have mentioned S as short beat and L as long beat. So if I play it like this, let us assume that I'm a music teacher. If I play it like this is a short beat, all right? This will be a short beat. This will be a long beat. So basically, a short beat consists of only one syllable, and long beat consists of two syllables. Short, long, short, long, long, short, long, short, long. So, so if I assume that I'm a music teacher and you guys are learning music from me, let us assume that. If we assume that, and I'm playing a chord, I'm playing the guitar or whatever instrument I have, and I leave gaps in between. So, for example, if I'm going to use different permutations of short and long beat, I would definitely make a music. Short, long. So a lot of musical chords can be made just by using the short beat and the long beat. So if I'm creating a chord, a musical tone, a tune, and in between I leave some spaces. For example, I'm playing a music. There's a musical note, again a musical note, again a musical note, and then I leave a space blank. Then a musical note, then a musical note, and so on. So this short beat can be filled in one blank, and if I leave two blanks, then you can fill it with either two shorts or one long. Is this clear? Is this clear to you? I'm repeating. If I am leaving just one space, you can fill it with one short beat. If I'm leaving two spaces, you can fill it with either two shorts or one long. If you understood this part, then we'll move ahead. Just show me a thumbs up in case you have understood this. Why not two longs? Diksha will do that as well. Basically, two longs. Okay, the space that the long beat is taking is two spaces. That is why. So let's say if I have four spaces empty. If I have four spaces empty, then in that case I can fill it with two different longs. All right. If there are four empty spaces, four vacant spaces, I can fill it with two longs or four shorts. Okay, I am repeating once. If there is one empty space, you can fill it with one short. If there are two blanks, you can fill it with either one long or two short. So basically, one short note takes only one space, one long note takes two spaces. I hope this is clear, Bharat. Sahil, galat link open ho gaya. You will actually be enlightened today. So this is clear to everyone. Now, I have made a table in which I have shown blank spaces and ways of arrangement. So these are the blank spaces, like one dot would represent one blank space, two dots would represent two blank spaces, and so on. So now comes the brainstorming, now comes the calculation part of it. So you guys have to tell me that if I have one blank space, in how many ways can I arrange the tunes? Now this is very simple. Everybody will say there is only one way, right? And that one way will be filling with one shot. So if I try to fill this blank, I can fill this with one shot. That's it. So there is only one way of arrangement for one shot. Sahil, parking question. Yes, right, right. One way is there, Deksha. Okay, good. Bharat, very good. Richa, great. Now, I won't be calculating it. You have to calculate. Tell me how many ways will be there for two blank spaces. We have to fill this, the ways of arrangement. Let's do that. I'm waiting for the comments. Let's see how many of you get that correct. Gaurav says there should be two ways. Which are those ways, Gaurav? Okay, all people say it's two. Akash says two short or one long. Very good, very good. There are two ways. There are two ways. Like I can fill with two shots, or I can fill with one long. Perfect. There are two ways for doing it. Now coming to three blank spaces. Piyush, basically there are blank spaces, and if you want to fill a blank space with one shot, S means short beat. So short beat takes one space, long beat takes two spaces. That's it. Now coming to the third, when there are three spaces. How many ways will be there? You guys are telling me the ways. Now tell me the number of ways. Some people say, Muskan says one long, two shots. Okay, a lot of people say that. Two long, two shots, one long, two shots. All right. Okay, so one of the ways is that I'll fill all these blank spaces with three shots. That is one way of filling it, all right? Then I can fill it with long. First two with a long and then with a short. And again, first one with a short and the other two with a long. All right? So it's short, 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 long, and long, short. So overall, we have three ways over here. Okay, so the people who are saying one short and one long, they can also reverse it. Like in the notes of music, as you can see, if I play one short and then one long, it will be different from, audibly, it will be different from one long and one short. So this will be three different ways. Now coming to fourth one. This can be difficult. Now tell me how many ways will be there to fill four blank spaces by using short, long simultaneously. Sahil says it should be 5. Very good, Sahil. Perfectly done. There should be 5 ways here. I can fill all 4 spaces with shots. So 4 shots can fill the space. That is one of the ways. Bharat, yes, we need consecutive space for long, right? This is one of the ways. The other way is I can use 2 shots and a long, and I can rearrange this short, short, long. 2 short, 1 long, I can rearrange. So I can write short, long, short. I can also write long, short, short. So there are 3 ways of using 2 shorts and 1 long here. Apart from that, I can use 2 longs. So if I count the number of ways here, it will be 1, 2, 3, 4, and 5. All right? So here, when we are doing this, we are also, some people can miss, some parts of it. But now when we're doing it chronologically, we are also getting an idea how to arrange things systematically. All right, this can help you with permutations and combinations. Now coming to the last one. That can actually be very difficult when we have 5 blank spaces. Do this. I'm waiting for some great answers over here. Diksha has given the entire thing. Very good, Diksha. Now, what about 5 ways? Five blank spaces. SLS is not possible. Someone says that. Why not, Akash? It is possible. Like first space in short, two next two in long, and then a short. It is possible. Yeah, Richa, Naveen, very good. That will be 8 ways. Good. Fakruddin says 7 ways. No, there'll be 8 ways. Now let us do that. There will be 8 ways. First way is filling all the empty spaces with 5 shots. That is one of the way. After that, now see, it's very easy. I filled with 5 shots. Now I want to introduce one long beat over here. So if I introduce one long beat over here, first 2 vacancies get filled up, and now next 3 will be shots each. So long, short, short, short. Similarly, I can just rearrange this one long. So I can write short, long, short, short. Similarly, I can write short, short, long, and short. And then I can write short, 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 long. So now my cases in which I used only one L and 3 S's are exhausted. Now I want to introduce 2 L's. Long, long, short. If I introduce 2 L's, then these 2 pairs will be filled by long, this by long, and this by short. And I can rearrange it again. So LLS is there. Then I have LSL, then I have SLL. Now let's count. How many are they? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 ways of doing this. So almost all of you got it correct. I'm very, very happy that you guys understood this. Now, there is very important observation over here. This is what Hemchandra did. You know, back in 12th century, Hemchandra was doing this. Now, look at the kind of intellect and imagination those guys had at that time. So he looked at this. He was basically trying to create a musical note. And then he realized that any number in this series, if I write it like this, 1, 2, 3, 5, 8, any number in this series is basically the sum of preceding 2 elements. So 3 is sum of 1 and 2. All right. 5 is sum of 2 and 3. 8 is the sum of 3 and 5. This is what is happening over here. All right. So every element in this series is basically the sum of the preceding 2 elements. Cool. So now if I ask you without even calculating or imagining, what if there were 6 spaces? What if there were 6 spaces? What would the answer be? If there were 6 spaces, what can be the answer? It will be 5 plus 8, 13. So I would like you, all of you to, when the session is over, try doing it for 6 spaces. Do you get 13 or not? So it will always be there. Great. Great. So now we have learned this part of the session. Coming to the next one. And you know what? This has just flashed. This thing was done in 1150 AD. All right, 1150 AD, way back. And most of you, like somebody also commented that this is Fibonacci sequence. This is Fibonacci sequence. Now here comes the, I would say, the surprise or even a tragedy for us Indians that we did not preserve this or did not promote this the way Westerners did to Fibonacci. But in the capacity of me being a mathematics teacher, I'm just promoting this in ancient Indian mathematics. And no way I'm trying to demean Fibonacci. He was a great mathematician. Now, the next slide. 52 years later, the world got enlightened. All right. So 1150 AD was the time when Hemchandra's sequence was created. And after 52 years, that was in the 1202, beginning of 13th century. I'm going to topic 2, that is Fibonacci sequence. In 1202, this great man, Leonardo, his name was Leonardo. Pisa is a city, right, in Italy. So he was considered to be the most talented mathematician of Middle Ages. He did not just observe the Fibonacci sequence, he even used it in a lot of ways. So I'll show you that. And it is same as the Hemchandra sequence. The numbers are exactly the same. Like 1. If I write the entire sequence, it'll be 1, then 1, 2, 3, 5, 8, 13, and so on. This is how it goes. First of all, let us understand, and then I'll tell you different patterns in our observable nature, observable universe in which you will find these patterns. Now tell me, who likes flowers? Just show me a thumbs up. Who likes flowers? Sunflower, rose, etc., jasmine. No one likes flowers? Okay, I'll tell you a secret which a lot of florists, even the florists, do not know. The people who are selling flowers might not be knowing this. I'll tell you a secret. So whenever you go and buy some flower, just count the number of petals, and you'll be surprised. You'll be surprised to know that the number of petals in any flower would actually be one of the elements of this series. Sajjan sir likes lotus, petals and Fibonacci, right, Sahil? So whenever you go and you count the number of petals, so of course 1, 2 petals are not there. So if you count the number of petals and you see there are only 7 petals. If there are 7 petals, that means flower is not fresh. 1 petal has just gone away somehow. Okay, so this can be really strange for some people. Some people already know it. Well done. And let's say if you get something like 12, that means 1 petal is not there, it's missing. The next should be 21. So from 13 to 21, okay, from 14 to 20, it's not possible for any flower to have number of petals from 14 to 20. It is impossible. Isn't it weird, surprising, strange? So Fibonacci, when he created this series, he tried to observe it in the real world, the biological world, and there he found out that the petals are like this. Now, why it happens? What this answers what? What is the question? Now we have the answer. But why it happens? That is more important, and that is what is missing in today's education, which of course iQuanta is trying to fill the gap. That will tell you why it happens. But before that, let us look at one more example. This is the colony of honeybees. Honeybees. So in the colony of a honeybee, like inside a beehive, what happens? The male, which is called a drone, male. This red one is, this thing is male, and this is female. So males do not have a father. Males do not have a father. Sahil or Nikha chemisonis has 15 petals. That is because evolution, and somehow that flower grown on to have 15 petals due to evolutionary biology. That was the need of the evolution. So that can happen. That exceptions are always the part of evolutionary evolutionary biology. All right. Now, so look at this. Whenever you see a male, it doesn't have a father. The male is directly born from the mother. So a mother can have 2 children, a female and a male. When these two meet, they can have only female, not males. All right. So see, from the male, a female is born, but from the female, a female as well as a male is born. To understand this chart, we need to just keep one thing in mind, that a male bee doesn't have a father. Bhavya, very good. This is called as parthenogenesis. Well done. Are you from biology background? So this is how it goes. Now if you look at the generation, so this first male, it begot a female. So there's, in the first generation, there's only one member, then another member. Then the generation tree goes like this. And now we have two members, one female and one male. This male begets a female, and this female begets a male as well as a female. Now we have three members. Now we have three members in this generation. Just a minute. All right. So if you keep on looking at this, this branch, you'll realize that every time what happens, a Fibonacci sequence number is formed. This comes from parthenogenesis, and there are other examples as well. Some people already know it. I'm really happy to see such an intellectual crowd. Well, now I'll just tell you some examples. First, I'll change the slide. Okay, I'll do it here. Do one thing, like if I avoid the exceptions in evolutionary biology, most of the living organisms follow this. So if you look at a tree, if you look at a tree, any tree, how does a tree grow? The tree has one trunk. This is the root part. Then there is a trunk. If you look at this, except there are some walls, there is some hurdle, the tree cannot grow properly. In the normal case, if you go to forest trees which are growing properly, you will find there's one trunk, one set of roots, one trunk, then this divides into two branches. All right? And one of the branches divides in two and one does not divide. I'm talking about parallel thing. Here you can see there are two branches, and in this case we have three branches. So this is how all the trees grow. Isn't this beautiful? Now I'm sure that all of you, when you go back to your homes or after session is over, you'll just go and watch some tree and you'll find out that this is what is happening. Isn't this strange? So same thing happens here as well. Now this will divide in two branches. This will divide in two branches again, and this will not divide. So now we have 1, 2, 3, 4, 5 over here. It keeps on growing like this. Well, so if you guys understood this, just hit a thumbs up. And now we'll go to a question. This question is very much relevant to aptitude exams like CAT. The question says, a rope is cut in two parts in such a way that the ratio of the length of the rope to the longer part is equal to the ratio of the lengths of the longer and the shorter parts. Find the ratio. Sahil, right, leaves on stems as well. Now let us solve this question. I'll give you 2 minutes. Let's try and solve this. Done? Any answers? Ayush says it's 4:1. Okay, Ayush. Let's have some more answers. Naveen says it's 2:3. Okay, you understood the question, right? Ayush and Naveen, please read the question again, and try to verify your answers yourself. You'll get to know why it is wrong. Well, let me solve this now. So this is a rope. This orange part is a rope. There are two, it's divided in two parts. Let the two parts be like this, such that, okay, we have one longer part, let the longer part be A, and we have one shorter part that, let that be B. So here A is greater than B. That's what I have assumed. Okay? Nagabhushan, this question is from CAT actually. Rest of the things are based not a part of CAT syllabus. That this session is based at uh, increasing your ability and visualization for mathematics. And yeah, Kunal said there's nothing called CAT syllabus. Yeah, that's right. Now this question, this is for CAT. Let's solve it. Okay, so A is greater than B. It says, okay, what is the length of rope? The length of rope will be A plus B, definitely. There's no doubt about it. So the question says the ratio of the length of the rope to the longer part, that A plus B upon A, is equal to the ratio of the length of the longer and the shorter part. So this is the equation that we will be getting. I hope everybody has got this. Sahil, perfect. Yeah, Sahil's answer is correct. Very good, Sahil. So let me solve this. Now what I can do, I can write this as A by A plus B by A is equal to A by B. A upon A is 1. All right, then B by A and A by B. We have to find what? We have to find A by B. This is what we have to find. So let us say that A by B is equal to X. I have assumed A by B to be equal to X. Right, Hardeep? You got that correct here. So if I write this, I'll get, now A by B is X. That means it's reciprocal. B by A will be 1 by X. So I have 1 plus 1 by X is equal to X. Now I can multiply entire thing with X. This is what I'll get. And then we have to solve this. Solve for X and you will get your answer. Yeah. Now everybody please solve this. What is the answer now? To find the answer, we can use Sridharacharya's formula, which says minus B plus minus square root of B square minus 4AC whole upon 2A. So this is what we can use over here. Here A is 1, B is minus 1, and C is minus 1. Let's put in the values and get the answer. So this becomes 1 plus minus 1, square of minus 1 will be 1 only, minus 4 times AC, that will be plus 4, whole upon 2 into 1, that is 2. So we'll get 1 plus minus square root of 5 whole upon 2. Abhigyan has got the answer correct. Well, what is the square root of 5? What is the square root of 5? It will be somewhat close to up to 3 decimal places if I write 2.36 whole upon 2. This will be the square root of 5 approximately. I'm erasing this part of the board. Solve it, everybody. So, if I add, there are two answers, like adding and subtracting, we'll get 2. And of course, negative cannot be the value, so it will be positive only. 3.36 whole upon 2. This comes out to be 1.68, whatever follows. So this is what we get over here. Ashi, you missed this. Ashi, basically, you look at the equation, you'll be able to understand this. If you see the equation, that will be enough. The rope was cut in two parts, where A is the longer part, B is the smaller part, and the ratio becomes like this. Rope upon longer part is equal to longer upon smaller part. This is what I have done by assuming A by B to be equal to X. Okay, so this is what we get. Cool enough. Now comes the real thing. This ratio is known as the golden ratio. And I have seen a lot of aptitude questions based on golden ratios, majorly geometry. And I think we'll be doing some kind of DI set also based on golden ratios. Not in this class, of course, in some other class. So this is golden ratio. Now, next time if something comes like this, one long rope, so lot of things which resemble this kind of statements, the answer would most probably be this ratio, or somehow this ratio would be involved there. Now comes the next one. Topic 3, that is golden ratio. So we have now understood what golden ratio is, but where do we find this? Where do we find this? Everything is connected over here, interconnected. So when you saw this Fibonacci sequence, and so on, here if you try to find the ratio of the numbers, successive numbers from their predecessors, if you try to find it, like here the ratio is 2 upon 1, that is 2, 3 upon 2 is 1.5, 5 upon 3 is 1.6, 1.66, 8 upon 5 is 1.6, and so on. So if you keep on finding this, at some point of time, this will be equal to the golden ratio. We don't have to find that, just for the sake of understanding and information, I told you this. Now, Fibonacci sequence gives birth to, now the thing is, the question that I did over here supports the golden ratio concept. Same way, Fibonacci sequence supports the golden ratio concept. Now comes a very surprising observation in human body. Like if a human stands like this, spreading the legs and his arms, if he stands like this, and now if you try to find this length, let this length be B, the shorter one, and this be A, then you will find the question that I have just mentioned over here, it will be same as that question, the ratio will be same. Of course, the ratio can change a bit. And if the ratio is exactly same, 1.618, the golden ratio, then that body would be very attractive. So if you know some people who are bodybuilders who have attractive body physically, if you try to find it out, you will see that the ratio is very close to golden ratio. That means the creator, I don't know God is there or not, but the kind of creator, the software expert, who can be called as God, when he created that software, a lot of you are software engineers over here, you understand this part. The software is created, we are the hardware, the software goes inside and the hardware is created, and if there is some error, then the bodies get disoriented. So this is how all the human beings have been made. Well, that's not the end. If you look at the starfish, in nature, starfish is the most beautiful animal. Why? Because if you try to find out the ratio, it will be exactly the golden ratio. Okay. There are n number of things in which golden ratio is there. So let us do one thing. In the next class of reading comprehension, which I will take, we will have a complete reading comprehension passage about the golden ratio. So let us do one thing. That's your homework. When the session is over, when you get time, you start studying. So look at the various examples of golden ratio that we'll be doing in this. Okay? In the RC class. Cool. So that is all about it. And the last one, how beautiful is beautiful. For this, I'll just draw a diagram and that will be all. This is a human face, eyes, nose, lips. So from the eyes to the nose and from the nose to the chin, if you try to find out the ratio, if it is close to 1.618, the face would look very beautiful. And this is how we can quantify beauty mathematically. So beauty is no more subjective. It has become objective now. We can define beauty via mathematics. That is where I'd like to end this session. Hope you enjoyed it. Have a great evening. Bye-bye.